ओके वेलकम डियर स्टूडेंट्स। आज हमारा सेशन होगा सारे कंसेप्ट अभी तक जितना पढ़ाई किया ना वो सारे कंसेप्ट को फटाफट से फास्ट ट्रैक रिवीजन लगाना। So let's revise all the concept till now. आज के दिन तक जितना भी कंसेप्ट आप लोगों ने थर्मोडायनामिक्स में पढ़ाई किया वो सारे कंसेप्ट को बच्चों में आज फिर से रिवाइज करवा रहा हूँ ताकि आपके दिमाग में थर्मो बहुत अच्छे से क्लियर हो जाए। पर ये वीडियो देखने से पहले आप लोग 11 लेक्चर्स फिर से एक बार देखना। ओके, अगर नहीं देखा तो पहले लेक्चर से लेके 12वें लेक्चर तक सारे सेशंस फिर से एक बार देख लेना ताकि आपको पूरा कंसेप्ट अच्छे से दिमाग में चला जाए। ओके, थर्मोडायनामिक्स में हमने शुरुआत की थी सबसे पहले तो सिस्टम नाम के वर्ड से। सिस्टम क्या होता है? तो सिस्टम जो चीज अंडर द इन्वेस्टिगेशन होता है उसे बोला जाता है सिस्टम। रिमेनिंग आर नोन एज अ सराउंडिंग। जिसपे इन्वेस्टिगेशन चल रहा है उसे बोला जाता है सिस्टम एंड बाकी का बचा हुआ पोर्शन उसे बोला जाता है सराउंडिंग। तो ये दोनों वर्ड्स बहुत ज्यादा इंपॉर्टेंट थे। उसके बाद था सिस्टम के डिफरेंट टाइप्स जिसमें था ओपन सिस्टम, उसके बाद था क्लोज्ड सिस्टम, उसके बाद था आइसोलेटेड सिस्टम। मैं उतनी ही चीजें आपको यहाँ पे क्लियर करवाऊंगा। आपको इसमें पीएचडी करना नहीं है बच्चों, उतना ही रेडी करो जिससे आप जेईई या नीट के लिए थर्मोडायनामिक्स अच्छे से कर पाओ। ओके, सो सिस्टम आएगा बेसिकली तीन टाइप से, ओपन, क्लोज, आइसोलेटेड। अब ये ओपन सिस्टम क्या होता है? जहां पे मास एंड हीट ये दोनों का एक्सचेंज पॉसिबल हो उसे बोला जाएगा ओपन सिस्टम। क्लोज सिस्टम किसे बोला जाता है? जहां पे क्लोज सिस्टम मतलब मास एंड हीट दोनों में से किसी का भी एक्सचेंज पॉसिबल नहीं होगा सराउंडिंग के साथ। एंड आइसोलेटेड सिस्टम मास आइसोलेटेड किसे बोला जाएगा? तो मास वहां पे बच्चों जो होगा एंड जो हीट होगा वो एक्सचेंज नहीं हो पाएगा। एक चीज ध्यान रखना, क्लोज सिस्टम में हीट एक्सचेंज पॉसिबल हो सकता है। ओके, अब उसके बाद था बच्चों एडियाबैटिक वॉल। तो सबसे पहली बात आती है वॉल क्या चीज है? तो वॉल सिस्टम एंड सराउंडिंग को डिफरेंशिएट करती है। ओके, एडियाबैटिक वॉल मतलब कि उस टाइप की वॉल जो नेट हीट एक्सचेंज को जीरो कर दे, मतलब कि उस टाइप की वॉल जो हीट एक्सचेंज को अलाउ ना करे। ओके, उसे बोला जाता है एडियाबैटिक वॉल। ओके, देखो फंडामेंटल थिंग्स है, बहुत छोटी छोटी चीजें हैं। अगर आपने अच्छे से फोकस कर किया ना तो आप बहुत अच्छे तरीके से पूरा सेशन समझ जाओगे कि पहले लेक्चर से 12वें लेक्चर तक का पूरा से रिवीजन हो जाएगा। अब एडियाबैटिक वॉल के बाद हम पढ़े थे थर्मोडायनामिक प्रोसेसेस। थर्मोडायनामिक प्रोसेसेस कितनी टाइप की होती है बच्चों थर्मोडायनामिक प्रोसेसेस? तो सबसे पहली एंड सबसे इंपॉर्टेंट थी आइसोथर्मल प्रोसेस। आइसोथर्मल प्रोसेस। अब आइसोथर्मल प्रोसेस किसे बोला जाता है? अब प्रोसेस इन व्हिच टेंपरेचर रिमेन कांस्टेंट, T रिमेन कांस्टेंट, जिसमें टेंपरेचर कांस्टेंट रहता हो उसे बोला जाएगा आइसोथर्मल प्रोसेस। फॉर आइसोथर्मल प्रोसेस चेंज इन इंटरनल एनर्जी, डेल्टा यू का मतलब होता है इंटरनल एनर्जी। सो चेंज इन इंटरनल एनर्जी, चेंज इन इंटरनल एनर्जी, इंटरनल एनर्जी वो होगा इज इक्वल टू 0। ओके, ये चीज आप पढ़ के आए हो बच्चों। उसके बाद जो था आइसोकोरिक प्रोसेस। आइसोकोरिक प्रोसेस ये वर्ड सिर्फ और सिर्फ उस टाइम के लेक्चर में आया था, उसके बाद इस लेक्चर में रिपीट हुआ है। लेक्चर नंबर 2 में ये वर्ड यूज हुआ था, उसके बाद इस वाले लेक्चर में ये वर्ड यूज हुआ है। बीच के किसी भी न्यूमेरिक पे आइसोकोरिक पे कोई न्यूमेरिक नहीं आया। आइसोकोरिक प्रोसेस मतलब कि वॉल्यूम रिमेन कांस्टेंट, वॉल्यूम रिमेन कांस्टेंट। अगर वॉल्यूम कांस्टेंट रहेगा ना तो फाइनल वॉल्यूम इज इक्वल टू इनिशियल वॉल्यूम हो जाएगा, उस केस में डेल्टा V का आंसर 0 हो जाएगा। अगर डेल्टा V 0 हो गया सो दैट इंप्लाइज W इज इक्वल टू 0 होता है। ऐसा होने का रीजन क्या है? तो ये होने का रीजन है W इज इक्वल टू -P डेल्टा V होता है। पर किसके लिए ये इक्वेशन चाहिए? इनरिवर्सिबल के लिए। ओके, इनरिवर्सिबल प्रोसेस के लिए W इज इक्वल टू -P डेल्टा V होता है। एंड फॉर रिवर्सिबल ये इक्वेशन चेंज हो जाता था, याद है? यहाँ पे हम क्या करते थे कि यहाँ पे हमने लिखा था फॉर रिवर्सिबल आइसोथर्मल प्रोसेस W इज इक्वल टू P डेल्टा P को कन्वर्ट किया था हमने nRT के साथ, याद है? ओके, तो इससे हमने एक टर्म निकाला था 2.303 के साथ। ओके, अगर आप ध्यान से दिमाग लगाओ तो ये सारी चीज कैसे कैलकुलेट की थी वो फिर से एक बार समझा रहा हूं, बहुत ज्यादा इंपॉर्टेंट वाला क्वेश्चन हो जाएगा तो ध्यान रखना। ओके, अब देखो हम कैसे सॉल्व करेंगे इसे। सो W इज इक्वल टू लिखा PdV। ओके, W इज इक्वल टू लिखा PdV। अब यहां से अगर आपने PdV लिखा तो यहां पे आप लिखोगे nRT। अब टेम्परेचर तो कांस्टेंट है। ओके, टेम्परेचर कैसा है? कांस्टेंट है। तो यहां पे क्या हम ऐसा लिख सकते हैं, सो PV इज इक्वल टू nRT। अगर इस PV को मैंने कैपिटल V लिखा, स्मॉल tv को मैंने कैपिटल V लिखा, सो यहां पे P इज इक्वल टू बनेगा nRT बाय V। सो P का वैल्यू रखो nRT बाय V इनटू dV। ओके, n कांस्टेंट रहेगा, r कांस्टेंट रहेगा, t कांस्टेंट रहेगा, सो 1/v इनटू dV। लिमिट जाएगा vi से लेके vf तक का। सो nRT ये बनेगा बच्चों ln V, यहां पे आएगा vi, यहां पे आएगा vf। सो बच्चों यहां पे आएगा nRT ln vf माइनस ln vi, मतलब कि nRT ln vf बाय vi। अगर आप नेचुरल लॉग से लॉगरिथम पे जाना चाहो तो उस केस में आप यहां पे लिखोगे nRT मल्टीप्लाई बाय 2.303। अभी यहां पे जो बता रहा था ये यही चीज थी, पर मैंने इसको डिटेल में फिर से एक बार समझा दिया ln vf बाय vi। ये इक्वेशन आपको यूज करना है बच्चों जब आपका प्रोसेस कैसा हो, आपका प्रोसेस रिवर्सिबल हो प्लस आइसोथर्मल वाला हो। उसके बाद बहुत इंपॉर्टेंट एक चीज आप पढ़े थे जो थे फर्स्ट लॉ ऑफ थर्मोडायनामिक्स। फर्स्ट लॉ ऑफ थर्मोडायनामिक्स जो था Q प्लस W इज इक्वल टू U, ये आप पढ़े थे Q प्लस W इज इक्वल टू U। जैसे ही ये सारी चीजें आपने कंप्लीट की ना, वैसे ही तुरंत आपने एक नया कांसेप्ट एंथैल्पी देखा था। अब एंथैल्पी जो वर्ड स्टार्ट होता है यहाँ से बच्चे कंफ्यूज होना शुरू हो जाते हैं, सर एंथैल्पी क्या चीज है? तो एंथैल्पी बच्चों एंथैल्पियन वर्ड से आया था जिसका मतलब होता है हीट कंटेंट। हीट कंटेंट जिसे हम H इज इक्वल टू U प्लस PV से डिनोट करते हैं। H इज इक्वल टू U प्लस PV से हम बच्चे इसे डिनोट करते हैं। ओके, एंथैल्पी। अब अगर आप चाहो तो इसे इस टर्म में डेल्टा H इज इक्वल टू डेल्टा U प्लस, अगर आपने लिखा कि डेल्टा V इज इक्वल टू यहाँ पे लिखेंगे डेल्टा NGRT, तो यहाँ पे डेल्टा NGRT लिख सकते हो इस टर्म के और में। ओके, तो ये हो गया एंथैल्पी का इक्वेशन। इसके बेसिस पर भी बच्चों बहुत सारे क्वेश्चंस। ओके, एंड हमने ऑलरेडी एंथैल्पी के ऊपर से क्वेश्चन भी सॉल्व किया था। अब एंथैल्पी के बाद आया था फॉर्मेशन एंथैल्पी। फॉर्मेशन एंथैल्पी क्या होता है तो मैंने समझाया था कि किसी भी एक मोल कंपाउंड को बनाने के लिए जितना हीट आपको देना पड़ा, ओके, कोई भी 1 मोल कंपाउंड के फॉर्मेशन के दौरान आपको हीट देना पड़ा या फिर उसमें हीट रिलीज किया, वो डिपेंड करेगा कि प्रोसीजर कैसा है, एक्सोथर्मिक है या फिर एंडोथर्मिक है। तो उसे बोला जाता है उस रिएक्शन का फॉर्मेशन एंथैल्पी 1 मोल के लिए हो तो। अदरवाइज अगर आप रिएक्शन एंथैल्पी निकालना चाहो, रिएक्शन एंथैल्पी सिर्फ वर्ड्स बच्चों डिफिकल्ट है, सिर्फ वर्ड ही डिफिकल्ट है। अगर आप रिएक्शन एंथैल्पी HR निकालना चाहो तो आप लिखोगे प्रोडक्ट एंथैल्पी माइनस रिएक्टेंट एंथैल्पी। ये हो गया प्रोडक्ट एंथैल्पी माइनस रिएक्टेंट एंथैल्पी। ये हो गया बेसिक चीज। मान लीजिए अगर आपने इक्वेशन लिखा होता N2 + 3H2 gives 2NH3। मैंने एक चीज आपको समझाई थी बच्चों के एंथैल्पी जो होता है ना वो मोल्स पे डिपेंड करता है। मतलब कि अगर आपने मोल्स चेंज कर दिए, अगर यही इक्वेशन पर 2NO2 + 6H2 gives 4NH3 लिखा होता तो ये दोनों के केस में एंथैल्पी का वैल्यू आपको डिफरेंट मिलता, क्योंकि दोनों के केस में नंबर ऑफ मोल्स का वैल्यू चेंज हो रहा है। अगर पहले इक्वेशन के लिए अगर आप लिखना चाहो, सो रिएक्शन एंथैल्पी इज इक्वल टू प्रोडक्ट 2 मल्टीप्लाइड विद एंथैल्पी ऑफ NH3 minus 1 into enthalpy of nitrogen plus 3 into enthalpy of hydrogen। इस तरह से आप रिएक्शन एंथैल्पी का इक्वेशन लिख सकते हो। ओके, स्टैंडर्ड रिएक्शन एंथैल्पी का मैंने डिस्कस किया था कि अगर कोई भी चीज उसके स्टैंडर्ड स्टेट होगी तो उस स्टेट में उसका रिएक्शन एंथैल्पी 0 बनेगा। वहां पे हमने डिफरेंट एग्जांपल लिए थे, जैसे कि कार्बन का ग्रेफाइट स्टेट में होना मतलब कि उसका 0 एंथैल्पी स्टेट होना प्रूव करता है। ओके, तो ये सारी चीजें बच्चों आपके लिए फिर से एक बार मैंने फास्ट ट्रैक रिवीजन करा दी। ओके, कल से फिर हम लोग शुरुआत करेंगे नए सेशन से। एटोमाइजेशन पे जाना है, उसके बाद कंबशन पे जाना है, तो धीरे धीरे न्यूमेरिक्स पे भी जाएंगे। जितना वर्ड्स से मिलते रहोगे ना उतना वो वर्ड्स आपके लिए नया नहीं रहेगा, पुराना हो जाएगा। जितना रिवीजन लगाते रहोगे उतना कंसेप्ट अच्छे से प्रिपेयर हो जाएगा। आज के सेशन में आपको कोई नोट्स नहीं बनानी है। सबसे पहली बात तो ये, इसको सिर्फ और सिर्फ देखना था, देख लिया। कल से नया सेशन शुरू होगा। ये पूरा रिवीजन था 1 से लेके 12 सेशन तक का। ओके, सो थैंक यू डियर स्टूडेंट फॉर वाचिंग दिस वीडियो। डोंट फॉरगेट टू शेयर, लाइक एंड कमेंट दिस वीडियो। टेक अ स्क्रीनशॉट लेके रखो।
We saw in the last video that if we defined enthalpy H as being equal to the internal energy of a system plus the pressure of the system times the volume of the system, and this is an almost arbitrary definition, but we know that this is a valid state variable, that no matter what you do in terms of how you get there, you're always going to have the same value because it's the sum and product of other valid state variables. But this by itself isn't that useful or that intuitive, but we saw in the last video that if you assume constant pressure, and that's a big assumption, but it's not a unreasonable assumption for most chemical reactions, because most chemical reactions, we're sitting at the beach with our beakers, and they're exposed to just standard temperature and pressure, or at least some pressure that's not changing as the reaction occurs. If we assume constant pressure, we saw that the change in enthalpy, becomes the heat added to the system at that constant pressure. That P there is just to show you that, hey, this is just when this is assuming that we're dealing with heat being added at a constant pressure. Fair enough. So how can we use these concepts in any useful way? Let's say that I had some carbon in its elemental form as graphite, and I add to that, I have a mole of carbon, and I add to that 2 moles of hydrogen in its elemental form. It's going to be a gas, and it's going to be as a molecule, right? If I just have a bunch of hydrogen in its gaseous state, let's say in a balloon, I'm not going to have individual atoms of hydrogen. They're going to bond and form these diatomic molecules. And if I react them, I'm going to produce a mole of methane, CH4. But that's not all I'm going to produce. I'm also going to produce some heat. I'm going to produce 74 kilojoules of heat, plus 74 kilojoules of heat. When I produce that 1 mole, I'll do a lowercase k for the kilo. When I produce that 1 mole of methane. So what's happening here? So first of all, how much heat is being added to the system? And let's assume that this heat just gets released from the system, that this isn't an adiabatic process. I haven't insulated the system from anything, that this just gets released. It just goes away. It gets released. So my question is, how much, I started off with this container, I guess we could call it, that's at a standard it's at a fixed pressure, and maybe I had a bunch of, well, I wanted to do the carbon, I'll do it in gray. I have a bunch of solid carbon laying around, maybe some type of dust, and then I have some hydrogen, molecular hydrogen gas. Each of those dots is actually 2 hydrogen atoms. And then I don't know, maybe I shake it up or something to make them react, and then I get a bunch of methane. And then I get a bunch of methane. I get a bunch of methane gas. I'll do that in green. So now I just have a bunch of methane gas, and I released 74 kilojoules. I released 74 kilojoules. So how much heat was added to the system? Well, we released heat from the system. We released 74 kilojoules. So the heat added to the system, was minus 74 kilojoules. Minus 74. Right? If I asked you the heat released, then I would have said 74. But remember, we care about the heat added to the system. Is 74 kilojoules. And I just showed you that that's the exact same thing as the change in enthalpy. As the change in enthalpy. So how can we think about this? What is the enthalpy of this system relative to this system? Well, it's going to be lower, right? Because if you take enthalpy, so the change in enthalpy is the enthalpy of your final system minus the enthalpy of your initial system. And we got a negative number. We got minus 74 kilojoules. So this has to be lower than this by 74 kilojoules. So this enthalpy right here is less than this enthalpy right here. So if we were actually draw it on a diagram, if I actually draw the reaction, let's say that this is just, I don't know, this is just time or something. This is as the reaction proceeds, that axis. And on the y-axis, I'll draw enthalpy. So the reaction starts off at your initial enthalpy, Hi, and that's this state right here. So you start there. I'll do it in the yellow of that container. So this yellow, I'll do it right there. You start there. And then, I don't know, you shake it up, or I'm not going to go into the activation energy, so it might have a little hump and all of that, but who knows. But then we end up at our final enthalpy. We have this final enthalpy right here. After the reaction has occurred. That's this state right here. This is H final. So you can see you've had this drop off in enthalpy. And what's interesting here is that not so much what the absolute value of this enthalpy is here, or the absolute value of this enthalpy here is, but now that we have enthalpy, we can kind of have a framework for thinking about how much heat energy is in this system relative to this system. And given that there's less heat energy in this system than that energy system, we must have released energy. And to some degree, I told you that from the beginning. Right? I told you that energy is released. And the word for this we use is exothermic. Exothermic. Now, if you want to go the other way, let's say we wanted to go from methane and go back to its, you have to add heat into the reaction. You would have to, if you wanted to go backwards through this reaction, go upwards, you would have to add that heat content to get that positive delta H, and then you would have an endothermic reaction. So if a reaction releases energy, exothermic. If a reaction needs energy to occur, it's endothermic. Now you might be asking, Sal, where did that energy come from? So I started at this enthalpy here, and enthalpy has this weird definition right here, and then end up at that other enthalpy here. And as you see, enthalpy, the pressure we're assuming is constant. Let's say the volume isn't changing much in this situation, or maybe doesn't change at all. So most of the change is going to come from the change in internal energy. Right? There's some higher internal energy here and some lower internal energy here that's causing the main drop in enthalpy. And that change in internal energy is really a conversion from some potential energy up here into the heat that's released. So there was some heat that was released, 74 kilojoules. And so our internal energy dropped. And what all of this does is it gives us a framework so that if we know how much heat it takes to form or not form certain products, then we can kind of predict how much heat will either be released or how much heat will be absorbed by different reactions. And so here I'm going to touch on another notion, the notion of heat of formation, or sometimes it's change in enthalpy of formation. So the way they talk about it is the change in enthalpy of formation, and it's normally given at some standard temperature and pressure. So you put a little, usually it's a knot, sometimes it's just a circle in there. And what that is how much, what is the change in enthalpy to get to to get to some molecule from its elemental form. So for example, if we want it for methane, if we have methane there, and we want to figure out its heat of formation, we say, look, if we form methane from its elemental forms, what is the delta H of that reaction? Well, we just learned what the delta H of that reaction was. It was minus 74 kilojoules, which means that if you form methane from its elemental, building blocks, you're going to release 74 kilojoules of energy. That this is an exothermic reaction. Exothermic reaction. Because you released heat, you also have this, you can kind of say that the methane is in a lower energy state, or it has lower potential energy than these guys did. And because it has lower potential energy, it's more stable. I mean, one way to think of it is, if you have a guy, you have a mountain here, and then it's down here, and you have a ball. You have a ball, and this isn't, a complete direct analogy, but the analogy to potential energy is, look, when you're down at a lower potential energy state, you tend to be more stable. And so in the everyday world, if you have a bunch of methane sitting around, the fact that it has a negative heat of reaction, or a negative heat of formation, or a negative, I should say standard heat of formation, because I have that knot here, or a negative standard change in enthalpy of formation, those are all the same things, tells me that methane is stable relative to its constituent compounds. And actually, you can look these things up. You'll never have to memorize them, but it's good to know what they are. And I copied all of this stuff. Actually, let me get the actual tables from Wikipedia down here. I copied all of these directly from Wikipedia. These give you the standard heat of formation of a bunch of things. And if you look down here for, let's see if they have methane right there. This is what we were dealing with. They're telling us essentially the delta H of the reaction that forms methane. They're telling us that, this point table right there tells us that if we start off with some carbon in a solid state plus 2 moles of hydrogen in a gaseous state, and we form 1 mole of methane, that if you take the enthalpy here minus the enthalpy here, so the change in enthalpy for this reaction at standard temperature and pressure is going to be equal to minus 74 kilojoules per mole. And this is all given per mole. So if you have a mole of this, 2 moles of this, and to form 1 mole of methane, you're going to release 74 kilojoules of heat. So this is a stable reaction. Now there's a couple of interesting things here, and we'll keep using this table over the next few videos. You see here, monoatomic oxygen has a positive standard heat of formation, which means it takes energy to form it, right? That if you have a reaction, let me just say the reaction, I'll write it this way, 1/2 of molecular oxygen as a gas to go to 1 mole of oxygen just as a kind of in its gaseous state. This tells us that this state has more potential than this state. And in order for this reaction to occur, you have to add energy to it. You have to put the energy on the other side. So it has to be, you would put a plus. So right here, you would have to say plus 249 joules. So you might say, hey, Sal, that doesn't make sense. Oxygen is just oxygen. Why is there a heat of formation of oxygen? And that's because you always use the elemental form as your reference point. So oxygen, if you just look, if you just had a bunch of oxygen sitting around, it's going to be in the O2 form. If you have a bunch of hydrogen, it's going to be H2. If you have a bunch of nitrogen, it's going to be N2. Carbon, on the other hand, is just C, and it tends to be in its solid form as graphite. So all heats of formation are relative to the form that you find that element when you have a pure version of it, not necessarily its atomic form, although sometimes it is its atomic form. Now, in the next video, we're going to use this table, which is a very handy table. I cut and pasted parts of it to actually solve problems. In this last video, I gave you the heat of formation, and we just thought about it a little bit. In the next few videos, we're going to use this table that gives us standard heats of formation to actually figure out whether reactions are endothermic, meaning they absorb energy, or exothermic, meaning they release energy, and we'll figure out how much. This problem is from Chapter 5 of the Kotz, Treichel, and Townsend Chemistry and Chemical Reactivity textbook. So they tell us, suppose you want to know the enthalpy change, so the change in total energy, for the formation of methane, CH4, from solid carbon as graphite, that's right there, and hydrogen gas. So we want to figure out the enthalpy change of this reaction. How do we get methane? How much energy is absorbed or released when methane is formed from the reaction of solid carbon as graphite and hydrogen gas? So they tell us the enthalpy change for this reaction cannot be measured in the laboratory because the reaction is very slow. So normally, if you could measure it, you would have this reaction happening, and you would kind of see how much heat or what's the temperature change of the surrounding solution. Maybe this is happening so slow that it's very hard to measure that temperature change, or you can't do it in any meaningful way. We can, however, measure enthalpy changes for the combustion of carbon, hydrogen, and methane. So they're giving us the enthalpy changes for these combustion reactions, this combustion of carbon, combustion of hydrogen, combustion of methane. And they say use this information to calculate the change in enthalpy for the formation of methane from its elements. So anytime you see this kind of situation where they're giving you the enthalpies for a bunch of reactions, and they say, hey, we don't know the enthalpy for some other reaction, and that other reaction seems to be made up of similar things, your brain should immediately say, hey, maybe this is a Hess's law problem. Hess's law. And all Hess's law says is that if a reaction is the sum of two or more other reactions, then the change in enthalpy of this reaction is going to be the sum of the change in enthalpies of those reactions. Now, when we look at this, and this tends to be the confusing part, is how can you construct this reaction out of these reactions over here? And what I like to do is just start with the end product. So I like to start with the end product, which is methane in a gaseous form. And when we look at all of these equations over here, we have the combustion of methane. So this actually involves methane. So let's start with this. But this one involves methane as a reactant, not a product. But what we can do is just flip this arrow and write it as methane as a product. So if we just write this reaction, we flip it. So now we have carbon dioxide gas. Carbon dioxide gas, let me write it down here. Carbon dioxide gas plus, I'll do this in another color, plus two waters, plus two, if we're thinking of these as moles, or two molecules of water, you could even say, two molecules of water in its liquid state. That can, I guess you can say that this would not happen spontaneously because it would require energy. But if we just put this in the reverse direction, if you go in this direction, you're going to get two waters. I'll do that in a different, or two oxygens, I should say. I'll do that in this pink color. So two oxygens plus, and that's in its gaseous state, plus a gaseous methane. Plus a gaseous methane. So plus a gaseous methane, CH4. CH4 in a gaseous state. And all I did is I wrote this third equation, but I wrote it in reverse order. I'm going from the reactants to the products. So if I'm going from when you go from the products to the reactants, it will release 890.3 kilojoules per moles of the reaction going on. But if you go the other way, it will need 890 kilojoules. So the delta H here, I'll do this in a neutral color. So the delta H of this reaction right here is going to be the reverse of this. So it's positive 890.3 kilojoules per mole of the reaction. All I did is I reversed the order of this reaction right there. The good thing about this is I now have something that at least ends up with what we eventually want to end up with. This is where we want to get. This is where we want to get eventually. Now, if we want to get there eventually, we need to, at some point, have some carbon dioxide, and we have to have, at some point, some water to deal with. So how can we get carbon dioxide, and how can we get water? Well, these two reactions right here, this combustion reaction gives us carbon dioxide. This combustion reaction gives us water. So we could just rewrite those. Let me just rewrite them over here, and let me use some colors. So if I start with graphite, carbon in graphite form, so carbon in its graphite form, plus, I already have a color for oxygen, plus oxygen in its gaseous state, it will produce carbon dioxide in its gaseous form. it will produce carbon. No, that's a different shade of green. It will produce carbon dioxide in its gaseous form. And this reaction, so when you take the enthalpy of the carbon dioxide, and from that you subtract the enthalpy of these reactants, you get a negative number, which means this had a lower enthalpy, which means energy was released because there's now less energy in this system right here. So this is essentially how much is released. But our change in enthalpy here, our change in enthalpy of this reaction right here, that's reaction 1. I'll just rewrite it. Minus 393.5 kilojoules per mole per mole of the reaction occurring. So the reaction occurs a mole times. This would be the amount of energy that's essentially released. This is our change in enthalpy. So if this happened, we'll get our carbon dioxide. Now we also have, and so we would release this much energy, and we'd have this product to deal with. But we also now need our water. So and this reaction right here gives us our water, the combustion of hydrogen. So we have, and I haven't done hydrogen yet. So let me do hydrogen in a new color. That's not a new color. Let me do blue. So right here you have hydrogen gas. I'm just rewriting that reaction. Hydrogen gas plus 1/2 O2. Pink is my color for oxygen. 1/2 O2 gas will give us some water. Will give us H2O. Will give us some liquid water. Will give us some liquid water. Now before I just write this number down, let's think about whether we have everything we need. To make this reaction occur, because this gets us to our final product, this gets us to the gaseous methane, we need a mole, or we can even say a molecule of carbon dioxide. And this reaction gives us exactly 1 molecule of carbon dioxide, so that's a check. And we need 2 molecules of water. Now, this reaction only gives us 1 molecule of water. So let's multiply both sides of the equation to get 2 molecules of water. So if this is a 2, we multiply this by 2. So this essentially just disappears. You multiply 1/2 by 2, you just get a 1 there. And then you put a 2 over here. So I just multiplied this second equation by 2. So I just multiplied this. This becomes a 1. This becomes a 2. And if you're doing twice as much of it, because we multiplied it by 2, the delta H now, the change in enthalpy of the reaction, is now going to be twice this. So let's get the calculator out. It's now going to be negative 285.8 times 2. Because we just multiplied the whole reaction times 2. So negative 571.6. So it's negative 571.6 kilojoules per mole of the reaction. Now, let's see if the sum of these reactions actually is this reaction up here. And to do that, actually, let me just copy and paste this top one here, because that's kind of the order that we're going to go in. But you don't have to, but it just makes it hopefully a little bit easier to understand. So let me just copy and paste this. Actually, I could cut and paste it. Cut, and then let me paste it down here, that first one. And let's see now what's going to happen. Let's see what's going to happen. And to see whether the sum of these reactions really does end up being this top reaction right here, let's see if we can cancel out reactants and products. Or let's see what would happen. So this produces carbon dioxide, but then this mole or this molecule of carbon dioxide is then used up in this last reaction. So this produces it, this uses it. So those cancel out. Let me do it in the same color. So it's in this green. This reaction produces it, this reaction uses it. Now, this reaction right here produces the 2 molecules of water. And now this reaction down here, I want to do that same color. There's 2 molecules of water. Now this reaction down here uses those 2 molecules of water. Now, this reaction right here, it requires 1 molecule of molecular oxygen. This one requires another molecule of molecular oxygen. So these two combined are 2 molecules of molecular oxygen. So those are the reactants. And in the end, those end up as the products of this last reaction. So those actually, they go into the system, and then they leave out the system, or out of the sum of reactions, unchanged. So they cancel out with each other. So we could say that and that, we cancel out. And so what are we left with? What are we left with in the reaction? Well, we have some solid carbon as graphite, plus 2 moles or 2 molecules of hydrogen, molecular hydrogen, yielding all we have left on the product side is some methane. So it is true that the sum of these reactions is exactly what we want. All we have left on the product side is the graphite, the solid graphite, plus the molecular hydrogen, plus the gaseous hydrogen. Do it in that color. Plus 2 hydrogen gas. And all we have left on the product side, is the methane. All we have left is the methane in the gaseous form. So it is true that the sum of these reactions, remember, we had to flip this reaction around and change its sign, and we had to multiply this reaction by 2 so that the sum of these becomes this reaction that we really care about. So since this is the sum of these reactions, its change in enthalpy of this reaction is going to be the sum of these right here. That is Hess's law. So this is the fun part. So we just add up these values right here. So we have negative 393 point. No, that's not what I wanted to do. Let me just clear it. So I have negative 393.5. So that step is exothermic. And then we have minus 571.6. That is also exothermic. Those are both combustion reactions, which are, as we know, very exothermic. And then we have the endothermic step, the reverse of that last combustion reaction. So plus 890.3. Plus 890.3 gives us negative 74.8. It gives us negative 74.8 kilojoules for every mole of the reaction occurring, or that the reaction occurs a mole time. So there you go. We figured out the change in enthalpy, and it is reasonably exothermic. Nowhere near as exothermic as these combustion reactions right here, but it is going to release energy, and we're done.